First, we have an announcement for you.
Hey guys, this review today, 5 p.m. in this auditorium. We'll be going over your exam on Friday, so hope to see you guys there.
Make sure you look over the spring 2015 exam before you come.
Did you get that?
Spring 2015.
Review for you folks today who are interested. Right here, 5 p.m. Review will be conducted by these two folks, Colin and Aya, and they've asked that you pay attention to Exam 1 from Spring 13. Is that correct?
Yep.
Okay. All of that, again, is on the Sakai website. You can all go all the way back there till fall 07 or some damn thing. I don't know. Now then, you know about this? A goof on the information sheet, which unfortunately I didn't see when it was run. I'll make this correction. Very near the bottom of the acid column, just above water. You'll see the formula printed for this hydrogen phosphate ion. As you look at the patterns of Ka values, since the acids are getting weaker from top to bottom, at a glance you should realize that the Ka value typed 4.7 times 10 to minus 3 can't be right, because it has to be smaller than the Ka immediately above it. It should be 4.7 times 10 to minus 13. So please make that correction, if you will, on your information sheet. I expect to have that corrected for the information sheet copies, which we will distribute to you tomorrow for your use during Exam 1. Although I doubt that with the remaining lecture material that we'll get into chemistry of polyprotic Bronsted acids, which would involve species like hydrogen phosphate. I say again to you, exams and quizzes in class will never exceed class coverage. That's one more reason why it's so important for you to be with us. All right. For discussion periods 1, 2, 3, 4 today, you folks have heard about buffers and the stuff which led up to buffers, the stuff which picked up from our point of completion yesterday. Now, from our point of completion yesterday to buffers, in the notes you'll see there's a section on indicators. So we're going to go back to that section on indicators right now and talk about such. In the main, I like to do the conversation on indicators because I got a couple of demonstrations which relate to this chemistry, and it's not convenient, unfortunately, to do these demonstrations in the discussion gatherings. So page 1830, indicators. You're familiar with indicators. You've used indicators in 46 lab. You used indicators in 45 lab. Organic molecules, which behave as dyes. And very interesting dyes from a chemist's perspective, because the dyes which are used as indicators are dyes which are subject to change in color as a function of solution pH. Perhaps you've noticed that on page 16 in the laboratory manual for 46L. There's a table of the indicators which are available for your use in Chemistry 46L laboratory, showing you the indicators by name and the colors they show at particular pHs. Comment? And likely you noticed this, for example, with your work in assignment 1 in 46L. To see a significant change in indicator color, you usually need to subject a solution containing that indicator to a change in pH which is at least as much or as great as 0.5 pH units. Which is a rather substantial change in hydronium ion concentration. I trust you've recognized that a change in 1 pH unit corresponds to a change in hydronium ion concentration of how much? 10. So delta pH 0.5 corresponds to a hydronium ion concentration change of how much? The answer to the question lies in determining the log of what number is 0.5. The log of 1 is 0.0000 by definition. What's the log of 2? 0.3010. What's the log of 3? 0.4771. And if I take that to 1 sig fig, I get 0.5, don't I? What's the log of 4? Twice the log of 2. What's the log of 5? 0.6991. What's the log of 6? I don't need to remember that one, because that's a log of 2 added to the log of 3. What's the log of 7? 0.8451. What's the log of 8? I don't even remember that, because that's 3 times the log of 2. What's the log of 9? I don't even remember that, because that's a log of 3 multiplied times 2. What's the log of 10? 1.0000. Isn't that hard? Because you see, by keeping this information in my noggin, I can do pH arithmetic for simple solutions being those whose molarities are known only to 1 significant figure. I can do pH arithmetic for most of those solutions. Bingo, just like that. And you should too. You're going to have to churn your brain a little bit to do this, but so what? That's what you're here for. So, that's change in hydronium ion molarity by a factor of 3. Now let's take a look at the indicator, which likely is the most commonly used indicator in water solution. Bromethymol blue, shorthand reference HBTB. Are you familiar with the chemistry of HBTB? You use such in 45 laboratory. In the experiment we had you deal with regarding introduction to chemistry of bronzosylaric acid and bases. That was assignment 5, part 2. How many remember that? Why is it arguable that HBTB is the most commonly used indicator in water solution? Well, the most commonly tackled pH range, since we rarely use solutions that are more concentrated than 1 molar, is 0 to 14. So 0.0 is a hydronium ion molarity of 1. And 14.0 is a hydronium ion molarity of 1 times 10 to the minus 14, and a hydroxide ion molarity of 1. So, if I have a solution whose hydronium ion molarity is guaranteed to be in the range which we've just talked about, or which has a pH which is in the range 0 to 14. Why do I want to use HBTB first if those are the colors which it shows as a function of pH? I don't give a damn about acidic or basic. Why should I use this indicator first?
It'll give you about a pH of around 7. So
How do you know?
Because of the colors that it shows.
Well, wait a minute. I'm talking about, we got a water solution of a compound. You don't know if it's an acid or base. All we're telling you is that its pH is in the range 0 to 14. That's all we're telling you. Why should I use this indicator first? Because it does what? When you can only do 1 test at a time, the best you can do to reduce the subsequent number of tests you may still have to do is to divide by 2. That's the best you can do. So 0 to 14, what's the middle? 7. Bingo! That's why I use this indicator first. Got nothing to do with acidic basic character directly. But it is true that this HBTB analysis will tell us if the solution is acidic or basic. or possibly neutral, or something close to neutral. If I see a yellow-green color or a blue-green color. If I see a yellow-green color, then I got a pH which is bigger than 6 but less than 7. Blue-green color, bigger than 7 but less than 8. That's what I know. Question. Based on the data we have on the board and this ionization equilibrium for HBTB. Given that the color changes exhibited by this stuff is yellow to yellow-green to green to blue-green to blue. HBTB by itself, what color is it? Yellow or blue? BTB minus by itself, what color is it? Yellow or blue? I'm listening. HBTB is blue. Sounds like the jury is having a problem with itself. HBTB all by itself. Yellow? You're damn right. And BTB minus is blue. Hey, look what's happening here. As the pH is going up, the system is becoming less acidic and more basic. Right? And as this change in acid-base character is occurring, the color goes from yellow to green to blue. And if I take away H plus from this, which is what I do when I make the system what? Get more basic or more acidic? If I want to take H plus from this. If I want to take H plus from any acid, do I want to make the system more acidic or more basic? More basic. Bases take H pluses away. Okay? So as I take away H plus, I'm making the system more basic. And as I make the system more basic, I get a blue color. That guarantees this is the yellow stuff and this is the blue stuff. Now then, when I see with this indicator a color which is distinctly green, what is the concentration ratio of BTB minus to HBTB? In the main, this question is asking you, or in a way this question is asking you, when you were a little kid, did you play with watercolors? Or was everything with this damn computer? If you were my kid, 1 hour max with the computer. Then you're going to get your hind end outside and go run around like a kid is supposed to and get some exercise. But now, if you wanted to take time to read chemistry books, I said, oh, that's okay. You can do that. Okay. When you played with watercolors, how many played with watercolors? Oh, a good amount of you, that's good. For those of you who have not had this wonderful experience, go get some watercolors and forget that damn computer. If you got yellow stuff and blue stuff, what do you do with these stuffs to make green stuff?
Mix.
Mix them in what ratio? 1 to 1. So how does the BTB minus molarity compare to the HBTB molarity if I see green color with my indicator HBTB? They're equal. Wonderful. So with that, I asked a $64 question, or one of the $64 questions, regarding indicators and their chemistry. Give me the approximate Ka value for HBTB based on the information you see on the board. I want the Ka value for HBTB to one significant figure based on the information you have on the board. I want you to tell me what it is right now.
1 times 10 to the minus 7.
1 times 10 to the minus 7. Does anybody support that vote? I sure do, because that's correct. Now, for those of you who are not seeing this, take note. For HBTB, there's the Ka expression. Nothing fancy about that. And when with this indicator we observe green, how does the molarity of this compare to the molarity of this? They're equal. Bingo! So the Ka for any indicator is equal to the hydronium ion concentration observed for that indicator. When the concentration of the indicator acid, and the concentration of its conjugate base are equal. And that happens for this indicator at pH 7. That's when we see a green color with this indicator. Is that right? So, one times 10 to minus 7. I guarantee there's questions about this stuff on the exam. I know, because I already wrote the exam. Now I'm going to go back and massage the exam. I always make a working draft. Then I go back, and after I make a working draft, because I generate my exams with a very wonderful program called TEC. After I write in TEC one exam version, it immediately makes me 5 exam versions, scrabbling all the questions and scrabbling all the response orders. Does all that for me. And prints it all out in the most nicely, neatly spaced condition you'll ever see. That's not bad. Now let me make an announcement to you right now. As I told you on the syllabus, every now and then when I run these exams, I make mistakes. I apologize for this. And I don't want students penalized for my mistakes. So if you think, there's one thing I got to do with the exam, I forgot to do this. There'll be a directive caption which says, if for any question on the exam, you believe the correct answer is not given, like for a calculation, required problem, okay? The directive will go on to say, on your answer sheet, you take the answer sheet, turn it over, identify the question for which you think the correct answer is not given, and write what you think is the correct answer. Okay? That way you're protected if you recognize a question on the exam which I, the author of the exam, have forgot to supply the correct answer. And chances are, if you do that, not only will you get credit, you get some extra credit. Hey. But only do that if you have legitimate cause to believe that a question stated on the exam does not have a correct answer choice. All right? Now then, on we go. More indicator chemistry. This time dealing with my favorite mythical indicator, HGG, which is abbreviational reference for Gainesville Green. My expectations are some of you have experience with Gainesville Green. Probably not an indicator. But we'll worry about that later, won't we? You see, I was a student here too. 1967. I first traveled through Gainesville in March 1966. Might have told you this before. That trip involved traveling through Gainesville in March, which is beautiful, flowers, green grass, everything. People walking around in shorts, temperatures in the 70s and 80s. After I left the lousy, frozen North Toledo, Ohio, with sleet, miserable cold, 30s, gray skies. And then from there, our trip took us to Fort Lauderdale. On the beach. I said, that's it, I'm coming to Florida if I have to pick oranges for a living. Fortunately, I don't have to pick oranges for a living. HGG shows the same colors as HBTB, except the pH range is somewhat different. Which is a stronger acid, HGG or HBTB? I'm listening. Because the Ka value, at least to 1 sig fig for HGG, is what? I'm listening. The Ka value for HGG, 1 sig fig, what is it? I'm listening. 1 times 10 to the minus 6. Because this thing shows equal molarities for HGG, the parent indicator acid, and GG minus, its conjugate base species, where HGG is yellow and GG minus is the blue stuff. So when those are mixed in equal molarities, they show me a green color. I have a pH of 6, don't I? So 6.0 corresponds to a Ka value of 1 times 10 to minus 6. Now let's go to 1 molar Horvath-James. My mythical acid Horvath-James. 1 molar solution, 100 milliliters. I treat it with a drop or two of my HGG indicator, and I see a green color. That's a result of my HGG indicator treated 100 milliliters, 1 molar HJ solution. Question? Which acid is stronger, HJ or HGG, and by what factor? I'm listening. Are these acids of equal strength? I heard a couple of faint yeses and a couple of faint no's. Which acid is stronger and by what factor? Or are they acids of equal strength? All right, if we're accepting that they're not acids of equal strength, then one of them is stronger than the other. Which acid is stronger? Is it HGG? I see a few votes. Or is it HJ? I mean, how could any acid be stronger than Horvath-James? And look at how many non-votes I got. Non-votes. Non-voters, the price to take tomorrow's exam is $500. I'll be collecting at the door to Carleton after I review the film to find out who the hell didn't vote. Then after the exam, everybody who did vote comes with me to the local beer and pizza place. And we're going to party at the expense of everybody who didn't vote. That's a stronger acid. Now, by what factor? 10, 100? I heard 2 votes. One was 10, one was 100. Neither of those votes are correct. Anybody want to yawp the answer?
A million.
A million? You're right. But HGG is 10 to the 6th times stronger. 1 million times stronger than HJ. Can you prove it? Or is this a consequence of my having overused HGG? Based on its other application. Let's have a look. If you simply allow the information presented you to talk to you, you will get this. Okay, so far? There's Ka chemical expression for acid HJ. We have a solution which is initially 1 molar. And this is a solution with how many solutes? You see this label? How many solutes? How many solutes? 1, HJ, that's it. You got to understand what this stuff means. So let's apply this recipe. Remember this recipe which we established at the conclusion of our last gathering, in which those of you who already had discussion class have used again today? Okay? This treated solution, 1 molar HJ shows a green color, doesn't it? So what's hydronium ion molarity? 1 times 10 to minus 6, isn't it? And since HJ on a reaction with water, since HJ is the only solute, creates a hydronium ion molarity and J minus molarity, which compare how? You see the stoichiometry for this reaction in your mind's eye? HJ plus water, double arrows, hydronium ion plus J minus. So how do hydronium ion and J minus molarities compare? They're equal. Well then, hydronium ion molarity has been revealed to us to be 1 times 10 to minus 6 by this HGG indicator analysis. Then the J minus molarity is 1 times 10 to minus 6. Now, what's the M sub I value for HJ? 1. If I subtract 1 times 10 to minus 6 from 1, am I going to change 1? Good. So there's the approximate Ka for HJ. 1 times 10 to minus 12. And have we not recognized that Ka for HGG is 1 times 10 to minus 6? I guarantee that 10 to minus 6 divided by 10 to minus 12 is 10 to the 6th. 1 million. All done. We proceed. I've got here some sketchy notes regarding the questions which are stated in completeness in the notes. 1830. Methyl acid HA, 1 molar, shows a yellow color with HGG. That's all I know. So for 1 molar HA, can I say flatly what the pH is? There's my HGG table. One molar HA. Here I treated 1 molar HJS, our green color. Now I'm treating 1 molar HA, a different acid obviously than HJ, and I see yellow color. Can I say anything absolutely about the pH of this HA solution?
that it's less than 5.
All I know is
It's 5 or less.
that the pH is 5.0 or a lower value. Do you think it's a good bet that the pH is 5.0? That's a lousy bet. That's only one data point out of a whole slew of data points, all of which are smaller than 5.0, like 4.9, 4.8, 4.7, 4.6, 4.5, blah, 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 all the way down to 0.0. Because if HA is a strong acid, it's ionized 100%, and this solution will have a pH of 0.0, won't it? Now then, if I stipulate that the acid strength of HA and the acid strength of HGG are identical, then what's the hydronium ion molarity in this stuff? Or pH if you prefer. I'm listening. One times 10 to minus 3 is the hydronium ion molarity, which to me means the pH is 3.0. Are we mystified by this? Oh, here's where the erasers are. All right, let's turn this K expression into one that corresponds to HA. We have speculated or stipulated for this question that KAHA and KAHGG are the same. And the label on the bottle is 1. Well, m sub I minus x, if x is a value that's small enough so that when I subtract it from m sub I don't change m sub I. So I get 1 multiplied times this, take the square root, what do I get? What number squared is giving me 10 minus 6? 10 to minus 3, isn't it? Well, that's hydronium ion molarity, as well as the A minus molarity. Showing us that if it be true that KAHA and KAHGG are the same, then 1 molar HA will have a pH of 3.0. Because that's a pH corresponding to this hydronium ion molarity. Let this stuff talk to you. That's what you got to do. Now, believe me, I'm very sympathetic with you that as yet you haven't learned to let this stuff talk to you. That's why I do what I do, to have you learn how to let this stuff talk to you. Because I didn't ask for this 6-week rush gathering, but I was asked to teach it. And I guarantee when somebody says to me, here's a 46 class, do you want it? Ha ha! The answer is you're damn right. Absolutely and forever. I love this stuff. I wouldn't trade this, what I'm doing, for anything. I mean it. It's too much fun. It's too valuable. All right? Now then, what if Ka for HA is unknown? We took this one into consideration. If Ka for HA is unknown, is it likely that HA and HGG are acids of the same strength? That'd be a lousy bet. Only one data point out of a bazillion. Bazillion is one way to express infinity. Well, is it likely then that HA is stronger than HGG, or is it more likely that HGG is stronger than HA? Can I make a decision? The answer is you damn right you can make a decision. I want to know what the correct decision is, and then of course I want you to tell me why that's the correct decision. That's where the answer lies always. The understanding always lies in answering the question why. That's why under no circumstances will you ever get from me on any quiz or exam a question which invites you to give me back a piece of information I gave you. That is stupid and ridiculous. That's not learning at all. And programming you for Jeopardy is something I ain't gonna do, never. I'm programming you to become chemists. Now, few of you, if any, will become chemists, but this is chemistry class. And if you don't do chemistry in chemistry class, I don't know where the hell you're gonna do it. But I suspect you all know that about me by now. So I repeat the question, which acid is likely stronger, HA or HGG? Well, I'll tell you the answer. Now you tell me why that's the answer.
There's a much larger range of acidic pHs that can be and not be. To be stronger, it has to be between 0 and 6, which is much more likely than between 6 and
0 and 6. What color did I see with this HA treated solution? Yellow. That means the pH is 5.0 or a lower value. And would you bet that it's almost a flat guarantee it's a lower value? Because that's only one data point. 4.9, 4.8, 4.7, 4. Blah, 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 blah. Okay? Now then, if HGG is a stronger acid than HA, then the pH of this HA treated solution, which is 5 or lower, is in there. Because at 3.0, HA and HGG are acids of the same strength. Didn't we already deal with that one? Now, when we get to the other side of 3.0, let's just take it to 0.0. So in increments of pH units equal to 1. 5, 4, 3. 3, 2, 1, 0. There's 4, and here's only 3. And it could even, well, it can't be. It's 1 molar. The pH can't be any value lower than this. Because if I got hydronium ion molarities greater than 1 molar, the pHs are negative. Okay? So it's a better bet because there's more data points in here. That HA is a stronger acid than HGG. No guarantees, but it's a better bet. Now then, question 1831. We stipulate that 10th molar HY, another mythical acid, and half molar HZ each show yellow with HGG. Can we make any can we make any decisions regarding, or from this information, regarding the relative strengths of HY and HY and HZ as Bronsted acids? Can we say anything about their relative strengths? Can we? Absolutely not. Because if I see yellow, hey, all I know is that I got a solution which is showing me a pH of 5.0 or less, just like with the HA solution, the analysis of which we just completed. Okay? Now then, can you make a statement which is indicative of which of these acids is likely stronger? Which is likely stronger?
More concentrated.
Which is likely the stronger acid? Which is likely the stronger acid? HY or HZ? HY. Isn't it at the lower concentration? And it's showing me an acidity which at things presently stand is comparable to the acidity shown me by the more concentrated solution. Now, I don't know for sure. We go to 1832. If I stipulate, this is going back to HA, that A minus is a weaker Bronsted-Lowry base than Y minus. What does this tell me about the relative acidities of HA and HY? Which is the stronger acid? HA. That's conjugate theory talking to you. If HY is a stronger acid than HZ, then I can say absolutely and for sure that the base strength of Z minus exceeds the base strength of Y minus. Period. That's what the conjugate base theory is all about. That's the way the acid base table is constructed, as it has to be. All right? Now up here we talked about 1 molar HA showing me a yellow color. But we never did decide what actually is the Ka for HA. We were not supplied with enough information to make that decision. But if I say that A minus is a weaker Bronsted base than Y minus, and I treat 10th molar HA with HGG, because up there was 1 molar, here it's 10th molar. Can I say for sure what color this solution will show me with HGG treatment? Can I say for sure what color will be shown by 10th molar HA?
Yes.
On treatment with HGG. What is that color?
Yellow.
Yellow. You agree with that? It is all an exercise in logic applied to chemistry. Because logic, what you have to apply to anything to understand it. All the time. It doesn't make any difference that it's chemistry or not. Look. A minus. Weaker base than Y minus. That means HA is a stronger acid than HY. And 10th molar HY, the weaker acid, shows me a yellow color. Well, then 10th molar HA is damn sure going to show me a yellow color. It's putting the puzzle parts together. It's like saying if Joe is taller than Sam, and Sam is taller than Larry, then how does the height of Joe and Larry compare? You know. Same thing. All right, now let's have some fun. We've been having fun all along. Let's have more fun. Here I have before you 6 solutions. 3 cylinders containing yellow solutions, 200 milliliters volume in each, and 3 flasks containing blue solutions, 200 milliliters volume in each, and for each solution the solvent is water. Now then, 200 milliliters blue, 200 milliliters yellow, okay? To intensify, oops, forgot to get my beat. Let me get some more indicator. I want to make the colors nice and intense. I'm now going to combine the contents of flask A with cylinder A. 200 milliliters blue water solution, 200 milliliters yellow water solution. Predict the colorimetric outcome.
Green.
The damnedest looking green I ever saw. Let's try this investigation one more time. 200 milliliters blue aqueous solution, 200 milliliters yellow aqueous solution. Intensify, color. Color prediction.
Green.
That's 2 strikes against you. One more time. And now before I make this mix, I will ask the $64 question. On making this mix, can you say for sure what the colorimetric result will be? No. That's correct. Ha 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 ha. Green. Now what do we know? We know that the mixture we made in cylinder C put together hydronium ion with hydroxide ion, because this is HBTB indicator I'm using here. Remember HBTB? Green at pH 7. So the mixture I made in this cylinder put together hydronium ion and hydroxide ion, where the hydronium ion molarity was higher in the cylinder initially, and hydroxide ion molarity was higher in the flask initially. So I put together the hydronium ion hydroxide ion in making this mixture in what ratio? 1 to 1, you betcha. But all I know over here now, after I made the mixtures, is that here, moles of hydronium ion in the acid solution exceeded moles of hydroxide ion in the base solution. And exceeded to the extent that I wound up with a solution where the pH is 6.0 or lower. And here for cylinder B, I now know that hydroxide ion molarity in the initially blue solution exceeded the hydronium ion molarity in the initially yellow solution, to give me a solution whose pH is 8.0 or above. Now then, let's clean up a couple of these cylinders. And we want to do one more investigation that has to do with 18 1834. Question 1834. Deionized water. This spigot here with the white knob on the handle as opposed to this one with the green knob, this is tap water. This is our deionized water. pH is probably around 6.5, a little bit of absorbed CO2, probably get a little bit acidity. Like you'll not find that your deionized water in laboratory is usually a little bit on the acid side. Gainesville tap water. Based on work you've already done in laboratory, what do you find the pH of Gainesville tap water to be, roughly? I'm listening. 8? I usually find about 9.5. Is that toxic, poisonous? I've been drinking it since 1966, and I don't think I've been hurt by it yet. The Florida aquifer stands over a bed which is rich in carbonates and phosphates, fairly basic materials. That's why Gainesville tap water, Florida tap water in general, is fairly basic. Now you see the label on this bottle? 1 molar acetic. I want to collect a volume which is the same as my deionized water. Not bad. Now then, to perform this investigation, I'm going to use an indicator with which you are familiar based on your work in 46 laboratory assignment number 1, methyl orange. Remember the color change is shown by methyl orange as a function of pH? As the system gets more acidic, methyl orange treated solution approaches a distinct red color. But if you go in the opposite direction, I get a distinct yellow color. Okay? So again, let's use an abundance of indicator so that the colors are intense. What color is this? I like goldenrod. How's that? That nice color? Lipstick pink. Okay. Shorthand reference to methyl orange, not health maintenance organization. O for orange. We'll call 5.0 yellow orange. We'll take that as yellow orange. I don't feel like writing goldenrod. Waste too much of my chalk. Now comes the $64 Challenger. I'm going to mix these solutions. What color will I get and why? Before you respond, I will tell you that for this case you can tell me flatly what the color will be. Have we got it figured out? As soon as I clean this slate, so we have territory to write for the remaining considerations that we wish to make. So with this red-pink, we're in here someplace with this solution. And with this, we're down here or at a higher pH. What is the resulting color? Red? We're not taking that as red, we're taking this as red-pink. RP, red-pink. That's what this one is. How many vote for red-pink? How many vote for pink? How many vote for orange? How many vote for yellow-orange? Oh, we got votes all over hell and gone. So I think you will accept my statement before we make the mixture that only a few of you have voted correctly. Now before I make the mixture, do you recognize what we're combining here? Equal volumes, 1 molar acetic acid, right? And what did I put in this cylinder? Deionized water. So what, in essence, am I preparing by mixing these solutions? I'm listening. What am I preparing? I prepared half molar acetic acid, didn't I? I diluted 1 molar acetic acid by a factor of 2. And what do we know about the ionization extent of acetic acid when you take it from 1 molar to half molar? The ionization extent increases, doesn't it? So did I change the pH very much when I diluted the 1 molar to half molar? Hell no. That's why the color stayed pretty much the same as my original 1 molar acetic acid, which is now standing before you as half molar acetic acid. This kind of stuff you got to think about. And it all follows from what quality or property of any system. What do you always have to think about to make these analyses correctly? PSI! Right? 1 molar acetic acid, deionized water. If you forget PSI, you have no chance, none, zero. Because now you have placed yourself in a position where you know not the nature of the materials with which you are dealing. This isn't witchcraft. This isn't black magic. To have a chance to understand the chemistry of the system, you have to know what the hell is in the system. On we go. Based on the reports I have received, all folks who have met with discussion class so far have gotten through the material in the notes. The rest of you will get this, period 6 people, you'll get it. Which follows from where we departed yesterday up to buffers and including and through definition of buffers. Well, what's a buffer? It's a system, a solution, which serves what particular purpose? pH preservation. Okay? Now, in order to do that, what are the contents of a buffer?
concentrated weak acid.
I need to have an acid that's present at high molarity, and the most common way to prepare the buffer is the conjugate base of that acid present at high molarity. Now, most solutions are buffered at pHs in nominal ranges, so to speak, of about 3.0 to 11.0. Can I buffer at pH 0? How do I buffer at pH 0? I take a swimming pool and I fill it up with 1 molar hydrochloric acid solution. I'll do a good job of buffering at pH 0. I suggest strongly you do not swim in this swimming pool. Can I buffer at pH 14? Now fill up the swimming pool with 1 molar sodium hydroxide. If you swim in either, you're not going to be happy, to say the least. So that's what we're through. Now then, question 1837. We're going to jump to that, which you've all been through for those of you who have all so far met discussion class. Note, this recipe does not apply to buffers. Why not? Consider HXX minus buffer. To tackle this very important property of the buffer solution system, pH, because after all, it's a buffer solution is serving the purpose of maintaining pH, we need to take a look at this ionization equilibrium, because it gives me a handle on pH, because this equilibrium contains hydronium ion. Can I use a different ionization equilibrium? Sure. I can do this. Who cares? Because this is a pH-dependent term. So either of these equilibria apply to this buffer system. Because in my buffer solution, if it's an HXX minus buffer, my PSI will tell me that this is a principal species as well as this. That's why this doesn't apply. Because in a buffer solution, how will the hydronium ion molarity and the X minus molarities compare? In a buffer solution, how will the HX molarity and the hydroxide ion molarities compare? In a buffer solution. I'm listening. I made the solution by purposely dissolving within, for this buffer, a bunch of HX and a bunch of X minus, like sodium X minus, NaX salt. Okay? So I repeat my question. In this HXX minus buffer, how will the hydronium ion and X minus molarities compare?
X minus is going to be
I know they're not equal. Which one is far greater?
X minus.
X minus, I filled up the damn pot with X minus. And X minus is a base, right? So that's standing in the way of having a high hydronium ion molarity in the system. So I'll ask the question about HX and hydroxide ion. How will the HX molarity and hydroxide ion molarities compare? Which one of these is greater? Didn't I make the solution by dissolving a whole bunch of HX? Am I going to have a high hydroxide ion molarity in the presence of a solution that contains a hell of a lot of an acid? No. So HX molarity is a lot greater hydroxide ion molarity, and X minus molarity is a hell of a lot greater hydronium ion molarity in any buffer, like the HX X minus molarity. Or, put it in general terms, the conjugate base that's been dissolved, it will exceed considerably the hydronium ion molarity, as well as the conjugate acid or solute acid will have molarity far greater than hydroxide ion molarity. That's why this is no good, because there ain't no X squared up top. Right? What you got up top for this thing is hydronium ion X minus over HX. And I can write it here, which corresponds to KB, HX molarity times hydroxide molarity over X minus molarity. But these are hardly equal. This is much greater than this, because I've prepared the system by purposely putting a whole bunch of this in there as solute. So this is no good. All right? So we go to 1838. Take a look at 1838 in the notes. We're going to make an ammonium chloride buffer. Let's put the nuts and bolts of this on the board. Milliliters, 0.80 molar ammonia solution. 100 milliliters, 1.0 molar ammonium chloride solution. Okay? Now for this buffer, which is an ammonium ion ammonia buffer, it contains, because that's the way I made the system, more moles ammonium ion than it does ammonia. And when I write equations for reactions, because when I'm dealing with buffers, I have to pay attention to the chemistry which occurs when I treat that solution with an external source of H plus or an external source of base. External source of hydroxide ion, okay? So I'm going to have to write reaction equations. And reaction equations are what? Ratios of concentrations? Are reaction equations ratios of concentrations? What are reaction equations ratios of? Come on. A plus B react to make C plus D. Moles! So I need moles. So, what aspect of PSI must we always consider when we wrestle with buffers? QPSI. All right? So for this, I got 0.80 moles ammonia initially, and here I got 0.10 moles ammonium ion initially. Is this buffer solution acidic, basic, or neutral? Acidic, basic, or neutral? I'm listening. Has more moles of ammonium ion in it, doesn't it? Correct. What is the solution, acidic, basic, or neutral? Acidic, basic, or neutral? Basic. If I pay attention to what we talked about yesterday, and in so doing recall that Kb ammonia is Kw divided by Ka ammonium ion, I will find that Kb ammonia is 1.8 times 10 to minus 5, and Ka ammonium ion, as given in the acid-base table, is 5.6 times 10 to the minus 10. So which has the far greater ability to affect pH? Ammonia. It's a much stronger base than ammonium ion is an acid. Kind of sounds like double talk, doesn't it? But it isn't. Solute ammonia reacts far more effectively with solvent water than does solute ammonium ion. That's why this system is basic, independent of the fact that it has more moles of the acid solute than that of the base solute. Okay? Now then, question 1838 says, let's take this buffer solution and treat it with .020 moles of pure hydrogen chloride gas. Okay? what's going to happen? Is this not once again a case of writing an equation for an acid-base reaction? So we look at our PSI. Ammonia, water. I didn't write that down. Ammonium ion, chloride ion. Who cares about chloride ion? It has no impact on pH. And water. Okay? So what I've written here are the quantitative PSIs for the base component and the acid component of this buffer system, and the quantity of this strong acid, which I'm going to use to clobber this buffer system. My attempt is to make the pH come down. All right? Now before I add the HCl gas, how do I get a handle on the pH for this solution? Can I look at Ka ammonium ion? Can I look at Kb ammonia? Yes and yes. They're the components of this system. Either one works fine. And notice that if I look at Ka ammonium ion, does that give me an equilibrium which also involves the other component of this system, ammonia, other principal component? Or if I look at Kb ammonia, does that involve the ammonium ion component of the system? Yes. Either one is fine. Now if I want to talk about pH, I use the acid component, but it doesn't make any difference which you use. So I'm going to write Ka ammonium ion, 5.6 times 10 to the minus 10. Hydronium ion molarity, ammonia molarity, ammonium ion molarity. Okay? So before I put the hydronium ion in there, before I put the source of hydronium, before I put HCl in there, okay? Then up here, I can write 0.080, and here I can write 0.10. Now those are moles. Do I have to change, because these are concentrations, do I have to change those mole quantities to concentrations for this system? Because if I take time to do that, that means I'm going to take this up down here and divide it by the solution volume, which is 0.20 liters. And I'm going to take 0.080 up here divided by the solution volume, 0.020. Why the hell should I waste time dividing the top and the bottom by the same number? I don't want to do that. That's unnecessary arithmetic. So, the hydronium ion is (0.10) times 5.6 times 10 to the minus 10. Divided by 0.080. That's before I put in the HCl gas. You do the arithmetic. Okay? Now let's put in the HCl gas. What's the HCl gas going to react with? You got the inventory before you. With which component of this system will the HCl gas react with? Will it react with water? What will it react with? I'm going to put the HCl gas in there. What will the HCl gas react with? What do acids react with? The strongest base in appreciable amount or concentration in the system. And for this system, what does our PSI tell us? Ammonia! Hey, you've got to have the PSI in mind all the time. So here we go. Reaction extent. 100%. Hell, if this reacts with water 100%, it's certainly going to react with a stronger base 100%. Okay? So here I put in this much. So how much of this am I going to murder? All of it? Will I murder all the 0.80 moles? 0.080 moles? Hell no, I'm going to put in 0.020 moles. So here's what's going to happen to this. And what's going to happen to this? That's what's going to happen. So there's how I get my hydronium ion concentration before I added the HCl. And now after I've added the HCl, this becomes 0.12. This becomes 0.60, which tells me at a glance, I haven't changed the hydronium ion concentration very much. Is that not the way buffers behave? You're damn right. Now then, there are a few more problems in the notes that are on buffers. That will be covered in tomorrow's lecture class and will be fair game for the exam because buffers are included. We've told you about the nuts and bolts of buffers. The rest is just practice. So tomorrow you're going to get more practice. And when we get through that, then I'll draw the line for stuff for which you will be responsible on exam number 1.